Good morning, everyone. Let's go to start our last seminar of the year. We will finish this year with a golden key with, with Marie. It's a real pleasure to introduce her, our visiting, and our friend Marie. No,
thank you for the introduction. Yeah, I'll speak in English because my Spanish is so advanced. Though I got a suggestion in the beginning that maybe I can give a talk in Spanish, but no, I think like neither of us would enjoy it. So in the abstract, I promised to talk a lot of APS boundary conditions. So I will introduce this boundary condition and also give you like the whole concepts that are somehow connected to this. But in the end, I won't be able to deliver a proof of like some final things. So I might somehow come back to it at the very end if we have a lot of time. I will also talk a little bit about another boundary condition, and maybe that one is even like physically more interesting. So just some couple of words about the motivation. From what I remember from other talks, it was not very visible, this mark. So if it was really bad, you just tell me and I'll try to do something better. We start with some physical system. And what do I have in mind here is usually we can think, for example, of an electron, and in particular, an electron moving on some manifold, on some geometrical space. So let me just say, yeah. So what does our particle? What are the properties of our particle? It will move very fast, so I'll say it's relativistic. It will be a charged particle because we will consider some magnetic field. So if it was not charged, it would not really sense any of that. So charged. And another property which be a bit still like complicated for physical systems, but we will consider it's massless, so zero mass. So these are the this is the concept you have in mind, and now so this is the sort of like what the physicists might consider, and now we want to somehow put this in words of math. In particular, relativistic particles are described by the Dirac operator. So I will not talk completely generally about this operator because, for example, people introduce it in geometry, and it can get like very broad and this really wide. But for me, it will be just this operator in coordinates. Another thing that I will consider is that this particle, it's moving on some manifold, but if you are not very familiar with this concept, you don't have to be very scared because my manifolds are very simple. So it will be some subset in 2 dimensions. And in particular, they will be like plane. So it will be R2. And then I will remove some sets from this R2. So minus some omega. So I will talk about this concept a little bit later. So I can really write it in coordinates. There will be like x direction, y direction, and we have minus I, and then it's a diagonal operator, or maybe let me just write it first in more abstract language of the polymetrices. So there will be polymetric sigma 1, and let me just put it different, minus I dx, and polymetric sigma 2 minus I dy. So this is the case if we did not consider any magnetic field. But now I'll add a magnetic field. So if you think of our plane, the magnetic field will penetrate this plane in the perpendicular direction. And why I'm thinking of this is because if the particle is just contained in this plane, then if you have any other magnetic field, it would not really make any difference, because it would sort of like the other components of B, they would just try to move this particle out of this plane, but it's constrained to this plane. So this is the only case that might make sense. So to this magnetic field B, there is a corresponding vector potential, which I'll call A. So that'll be minus the X component of A and minus the Y component of A. So B is perpendicular to our plane, but this A, it's living inside. Yeah, let's just put it as this, inside the plane. Right. Couple of more remarks to this. So this A is unique. The relation A and B is given by, so that would be the X, A, Y. I never know like which one is first, dy ax. So this is a vector actually. So in fact, this is 0, 0, and then this component would be equal to 0, 0, and B. So this is again like some convention that I say that the X direction, Y direction are those that lie in the plane, and then the B has the Z direction. Let me just think. I think this is correct, the sign. So you might also remember from some other courses, like from physics, that if like a gradient of some function f, let's say f is smooth, then the rotation actually does not change. This would be the same as taking the rotation of A, because the rotation of gradient is just 0. So in this sense, the given a B, so the B is really the physical quantity, but given a B, we get various A's, and this sort of freedom is called the gauge freedom, and I will have a particular choice, which will be called Casher gauge, and I'll talk about it in a second. So that is one remark. There's another remark, but actually get to the next part. So I'll add this remark in a second. So we have a Dirac operator, and then we have a particle. So what do we do with that? The problem that we consider, that we are interested in, is considering so-called zero modes. So that is what I also did for my PhD, and that is sort of the main motivation. So the zero modes, what they are, as the name sort of suggests, they will be the eigenfunctions of this operator D, which corresponds to the value 0, to the eigenvalue 0. So there will be U such that D on U is equal to 0. So what is important for sort of like having some physical interpretation is that this U can be just anything that satisfies this equation, but we want that this U will belong to a set which we call the domain of D. So domain of D, if we just think, let's say, only about R2, we can take domain of D will be functions U that are square integrable, such that when we act with D, we again end up in square integrable functions. So these are functions on our manifold. So I'll just say R2 here. Why is it T2? Because this actually, I did not say properly here what these things are, but the sigma 1 and sigma 2, they are the Pauli matrices, and they are 2 by 2 matrices. So this is why we need two components that we act on. So let me just write what they are. This is the anti-diagonal 1, 1, and sigma 2 is minus I. So the domain of D is important for us, and in particular, for systems in physics, we want domain of D to be such that the operator is so-called self-adjoint. So if you are familiar with the concept, then you know. If not, then I might not get into details. It's the main point is that self-adjoint operators have real spectrum. So the energies, so this is like an energy operator, the energies that you would measure are real valued. So they're real numbers. Right. So now the other remark that I wanted to say here is that if the boundary of our manifold, so maybe I'll call this M. So if the boundary that I'll denote by this, the boundary of M is a non-empty set, then we cannot just take this set, we have to assume boundary conditions. So we need boundary conditions. And in particular, these boundary conditions again have to be such that this operator would be self-adjoint. And so as I promised in the abstract, one of the boundary conditions I'll be talking about is this APS. So it's called after Atiyah, Patodi, and Singer, who wrote a famous paper on index theorems. So that's another point where I'll return in a bit. And they use this boundary condition in their proof, or for the system that they use. Another boundary condition that I want to talk about, that I told you in the beginning of the talk, is the infinite mass boundary condition. Mass boundary condition. And you can think of this one as really the particle cannot really penetrate this boundary because it would just have infinite mass there. It would be like very, very heavy. Okay, we have this massless condition here, but it's just like as it really cannot go through. So these are these 2 points, and now I'll talk a bit more about these zero modes, how we get them. So there is, let's say, part 1, which is related to something that Aharonov and Casher did. So they were interested in exactly this question of zero modes, and they solved this problem for the case when we have just R2. So what they did was that they used the, it's not very somehow convenient for this, and rewriting this operator in complex notation means that we have dz bar here, dz, and then we have the vector potential. So there is minus IA half and minus IA half, but one of them has a bar. Which one? The top one. And the convenient thing is now that this operator is anti-diagonal, and because we want to solve this equation, so we act on U, we can just decouple this and have just 2 separate. Right, thank you. Minus do I? Yeah, thank you. It decouples into two equations. So we don't have to like these components of U. So U has values in C2. So it will be some U plus and U minus. And we don't have like any coupling between these two. They just don't communicate. And this is also because we have this assumption. In the case that we had mass, the mass will actually appear here as m and minus m. So this is also sort of great simplification for us, and the reason why we can sort of solve this. So what was the trick that Aharonov and Casher used? So let me just put it here. Aharonov, Casher. That was using an ansatz that U plus and U minus have a very specific form. So it was e to h of some function times some function g, and U minus was again e to, okay, maybe let me put minus h of times some function g minus. And if you put this one in here, you'll find this, that so this dz bar acts on U plus, so we have dz bar minus IA half. And now U plus is exponential of some function times another function. So let me just put it in. And then we the e to h on the other side. When dz bar hits the exponential, we get dz bar of h. Then dz bar hits e, so we get dz bar. And then this is just a scalar, so these two commute. We have minus I a half, and e to h now on the other side. What we do is that we choose this h so that this term cancels out this other one. So dz bar h is chosen in such a way that dz bar of h is equal to I a half. And indeed, one can do this, it's not a problem. And what we dz bar on h plus is equal to 0, but dz condition. So this just means that g plus is an analytic function, and analytic functions in R2 we just know them well. So it will just have some Taylor series. It will be, I mean, from this on R2 we can say that g plus is equal to some sum coefficients of complex coefficients an times powers of zn. And since we are in R2, this n will start at 0. So let me just say a couple more words about this part. So dz bar of h is IA half, and we can apply dz on this expression, which means that get Laplacian here. So I did not really say it explicitly, but what I mean by dz and dz bar is dx plus I dy half, and this one is just complex conjugate, the dz. So if you apply these two, you can just check that this actually is 1/4 of the Laplacian of h. And then if we apply it here, that's another thing that I actually did not say explicitly, but we started with a as a vector, but here I somehow transferred to this complex notation. So not only that we have dz bar is this, also the a sort of changed. So the not changed, but I mean another object with it, and about a without any errors or indices down there. I mean the this ax and this ay, they are real valued functions. And when we act on this with the z and have this part here, what we get is the magnetic field B, minus 1/4 of B. So this is just a computation. It's a very straightforward computation. And there is actually another other assumption that comes in that we can do because of this gauge freedom. In particular, our A will be such that divergence of A is equal to 0. So this is just choice. It can be done. So from this, if we now want to find this H, we take the green function of Laplacian. Yeah, I did not say what this B is. So we can just think of B being a smooth function that is, let's say, compactly supported. So I'll say that B lives only in somewhere here, and it's a smooth function. So for H, I can take the convolution of the green function for the Laplacian with the magnetic field B. So let me just remind you that the green function for Laplacian is minus 1/2 pi times log C in this case. So and so this is again some sort of choice, and with this choice of H, now I get back to A, what I call Aharonov-Casher gauge. So Aharonov-Casher gauge is a convenient gauge for solving this problem, because now we actually found these zero modes. We have this H, we have this T. Zero modes are of this form times this exponential e to h. So U plus would be e to h times t plus, which is given by this relation. And now more to this question of how many there are, because this is not the end of the story. All of these functions, they are not necessarily in this domain. They don't have to satisfy this condition. They will satisfy this condition because it's just 0, so that will end up in L2. But the condition that U is in L2, that's also important, and that's not present right now. So what we have to compare it to is how these zero modes behave at infinity. So we are in R2, and at infinity we want them to decay, and in particular, so that they would be in L2, they have to decay faster than Z inverse. So we look at how this e to h looks like at infinity. E to h behave. So this is just something that you see from this B. From as Z to some quantity minus phi over 2 pi. And let me just say what this quantity is. This quantity is called flux, magnetic field of magnetic field B. Okay. This is a 2-dimensional integral in the plane. The B is a real valued function, and I plane. And recall that here we just assume that the B would have a compact support and would be some smooth function. So it certainly has meaning, and this quantity will be finite. So e to h can be shown.
Entire
the phi is just a number.
Oh, okay.
Yeah, it's just a number. Just a real number. I take B, which is a function in R2, and I integrate over R2. Yeah. So this is just a real number, and then I have this G plus, so I just put this series, some A n Z to n, And now I count the powers of z, and I want that n minus z to this one minus phi over 2 pi, that this one is less than -1, and this or some n0. So n0 would be like, so if I have small indices, everything goes fine, but then if I go to a higher n, I have to cut these series off because of this, because I want this decay. So let me call just n0 the highest index, and I want that n0 is less than pi over 2 pi minus 1. So this is how you can count these zero modes. You know that now they have this form, and the n goes only up to a certain index, up to the index over 2 pi minus 1. Right. So in other words, how you can also rewrite this, that there are like the lower, so this is a real number. If it's an integer, then it will be that integer -1. If it's slightly higher than integer, then it will be like the lower, not saying the right thing. Right, sorry. This is correct, but I'm just thinking of this -1. So the number of the zero modes, that was the question, number of zero modes is now phi over 2 pi minus 1. Then I have this like strictly smaller, so I take the lower part, but then because I also have this is the highest n, but I also start from 0, so I also have +1. So in the end, the number of zero modes is just this number, the integer part of lower integer part of pi over 2 pi. Right. So this was what Aharonov and Casher did, and then what we did with my advisor for PhD, we considered slightly different setting. We considered R2, but now we have holes in R2. So the particle can move around, but it cannot move inside here. This is just a forbidden region for the particle. It just cannot go inside. So it's here. And then we have something like Aharonov and Casher they have like some magnetic field. So there would be again some B. And what we also had, like as an extra magnetic field, was magnetic field inside these holes. Sorry, maybe one more remark here. I don't know if you wondered, but I have two components here, U plus U minus, and so the upper component, the U plus, a very similar treatment holds for the lower component, and in particular, we would be looking for anti-analytic functions. So this is just a comment to this, and we would have zero modes U plus in case that this phi is positive, and we would have the zero modes U minus in case that this phi is negative. So it's the direction of the magnetic field. You can think of it as if it's sort of aligned with the magnetic field. So this is just one comment. And so back to this PhD thing. We have again some magnetic field, but we also assume that these holes where the particle is not allowed also have some magnetic field. And there is something sort of stronger than just this gauge invariances we had before. What one can show is that you can sort of modify the magnetic field inside, and it will not have any effect on the zero modes, in the sense that the Dirac operator is unit equivalent. If you change the magnetic field inside to whatever it is, as long as it has the same flux. This phi was the flux, but not only that, you can even change the flux by an integer times 2 pi. So if you started with some B1 here, which was, let's say, like this would be equivalent to the case that you have B, which is, let's say, just in one point, like a singular point, and it would have the same flux, phi1, plus any integer m1 times 2 pi. So these situations are equivalent. So we can just somehow relax to this situation, which is sort of easier to, which might be like more easier to treat. So that was about the Aharonov and Casher, and now I'll say a couple of words about APS boundary condition, and then I think we will just have time to finish. So this APS boundary condition, it was introduced in connection with this index theorem. So connection between that problem and index is that the index of D, or in particular of one of these components, would be, let me just introduce some notation. So D had these two components. So I'll call the lower component D plus and the other one S. And then index of one of these, of D plus, would be given by kernel of D minus the co of D minus of D plus. And what is this co-kernel? It's sort of the codimension of the range. So like you map to some space, and whatever is left, yeah, is the codimension of this space then. And what is important here, that this D plus and D minus, they are formally adjoint. And then what you can get here is that the co-kernel of D plus can be written as kernel of D plus adjoint, but that would be the D minus. So you get this difference. Sorry, I forgot something. So it's not the kernel; is just a space. This is a number. So what I actually mean here is the dimension of these spaces. Yeah. So if you compare it to what we had here, we looked at the number of zero modes, which is basically the number of the functions that we have in the kernel. And that means this is exactly the difference of the number of zero modes with spin up minus the number of the zero modes with spin down. And what this says is, so you can use this index theorem. It's like much heavier than this computation. It's really like more topological, and like nowadays there are simpler proofs that are more understandable, but it's much more difficult. And you can use their formula, which is a topological formula, and therefore one can see that this quantity is actually topological invariant. Like if you change something in your manifold but keep the topology, it will be the same. But you can compute that this would be exactly this number what we had. Okay. Okay, let me just not say more about this. The point is that this index theorem is for closed manifolds. This is not a closed manifold. So it's a bit like more subtle how to compare these two. But to compare them, what you can do, that you take your R2 and you wrap it on a sphere. And then you are allowed to compare these two. And you would get the, yeah, okay, now I'm actually not sure, there might be like some difference. But what Aharonov and Casher basically showed is that one of these contributions is just not there. It's just vanishing, because you just have magnetic field always with a flux of a certain sign. Okay, so they prove this index theorem in a bit more general setting. This more general setting was that they also had some boundaries. So it didn't have to be closed manifold, but you could have something, let's say, like this, for example. Like this. So this would be the manifold. You have some end here. And the boundary condition that they used here is the APS boundary condition. So what does it look like is that you take your Dirac operator here. So, and you rewrite it in a certain way. They assume that near the boundary, that the manifold has so-called product structure. So that is somehow related to the metric, that the metric has this product structure. And it's here, one invert normal, and the other one would this other direction, but we don't have to give it a name right now. So I'll rewrite this Dirac operator as some metric sigma. This one is not either of the sigma 1 or sigma 2, but they are sort of related. Then the direction of the normal, so the R, plus another operator. This other operator is just what is left over there. This is just a local expression. This is just like on this in this neighborhood where the manifold has this product structure. And what's left here is this B, which is again a Dirac, so sort of first order differential operator. This one acts on the boundary. So in our case, if it's two-dimensional, it will act on only on this sort of circle or whatever shape we have there on the boundary dm. This dr is then the invert normal derivative, and sigma is some sort of endomorphism on C2.
Sigma is just a factor.
Yeah, yeah.
Function.
Right. It, in principle, it can depend on the normal direction as well. But the
just put whatever is in front of your
yeah, right.
So locally the boundary, this is a kind of conformal equivalent to cylinder or something.
Yeah, the near the boundary, it should be basically it near the boundary. So this is the dm. This part is like dm times some interval 0r. Yeah, and there we can rewrite it in such a form. So what also we somehow, I did not say explicitly, but what we assume is that the boundary is a compact set. So the M is compact. And what this implies is that I have a Dirac operator on a compact set. What this implies is that this B has a purely discrete spectrum. So B discrete spectrum. And I can find the like basis of L2, which will be formed by the eigenfunctions phi j of B. So phi j B lambda j. And what I want is that the functions in my domain satisfy that if I restrict them to this boundary, they will be equal to sure, sorry. Yeah, sorry, thanks for telling me. I want that the, so let me just rewrite that the b phi j has eigenvalues lambda j, and I want that when I have a function in the domain restricted to this boundary, that they will be a linear combination of this phi j, some aj, but the j will be from the set such that lambda j is negative. So this is the boundary condition. It's sort of it's a like global type of boundary condition. It does not tell you what the function looks like at a certain point on the boundary, but it's like sort of formulates the behavior of this function on the overall of the boundary. And
the negative spectrum is finite or the other way around?
no.
It will be finite or infinite.
It will be up to like, it will be the whole integers. It will, I mean, the b will have, in our case, for example, it's really like the whole integers.
Oh, okay.
And you just cut it at one side. Yeah, so okay, yeah, I won't say more. But
The symbol is B, that could be.
okay, yeah. So in our case of these holes, like our b was just sigma 3, so that is 1 minus 1 times d phi minus ia phi, like this derivative in one direction. The a phi is just a function.
And
I
think.
right, yeah. Otherwise we would not have it. Right. Yeah. Does that make more sense? So let me finish with one point that about this Atiyah Patodi singer, which is that this is somehow like now I don't have the word in my mind, tailored so that these zero modes can be sort of extended. So I had this, so let me come back to this drawing. So I have this cylinder structure here, and now I think of this manifold being extended to the other side. So I had like r, the direction of r here, it was positive, and now I think that this r actually continues in this direction to minus infinity. And then what we can do is that we look at this equation, d of u is equal to 0, which is satisfied everywhere here. And using this equation, we sort of extend this u to the other side so that it's a L2 function again. And how do we do that? We rewrite this d in the same form as before. So we had this sigma, and then there was dr plus b acting on u. So in particular, now I think of u somehow extended to this direction. So it's not only on the boundary. So it will be function of r and another variable along the boundary. So let me just call this cylinder. The cylinder is dm times minus infinity to 0. So r is from this interval, and dm I introduce some coordinates. I parameterize it by a coordinate t. So u will be function of these two. If I have this product structure, what happens that this b depends only on this t. It does not depend on r, and that is sort of important. And I get that dr on u is equal b on u. So just solving this equation, I get that u can be written as the exponential e to There is a minus here, right? There is plus, there is minus. E to minus R, B, and now U at this boundary at R equals 0, dependent on T. But this was the boundary condition. So this was some of some linear combination of phi j such that lambda j, the corresponding eigenvalue, is negative. And then, so when B hits this, when B hits the phi j, it will just give me the eigenvalue lambda j, which is negative. So I get the exponential lambda j and sorry, aj phi j.
Some should be before.
Right, thank you. And now I have minus here. So minus lambda j is now positive, and R goes to minus infinity. So it decays exponentially in this direction. And that is like a nice property of this APS boundary condition. And that was something that we wanted to exploit and work with Hanne to somehow extend the result from the PhD thesis to holes which are not only circular but have a general shape. Was somehow using this idea that we can also extend them further, but we don't have this product structure, so things are getting a bit complicated, and we got into very technical details. So this was why I was not actually talking about this more explicitly. But yeah, okay. I guess I'll just finish here. Thank you for your attention.
For today. Does anyone have any question or comments?
So you extend you solve this problem to the left, let's say, then du equal to 0 to the left.
Mhm.
Then what do you do to the right?
So you assume that, sorry, this is extending a solution. So you assume that you have a solution here.
I have a solution.
Yeah, you have a solution, and then you just say this boundary condition is sort of tailored that the zero mode. This is only specific to the zero modes. But in principle, you also impose this boundary condition to like higher energies. But I've never heard of anybody looking into this problem. So yeah. Yeah, I mean, if like to each zero mode, you restrict the u to the boundary. So this is a unique function, and then this is the solution. So it's a unique extension. No.
So how do you get the solution? How do you get the solution to the left, to the right?
I mean, that is more complicated, I guess. This is why we have this assumption like that we really have just a plane or plane with holes where you can solve it explicitly, because in plane you also have this like beautiful form of the Dirac operator, and you have sort of a manual from Aharonov and Casher how to solve this. But if you have something more ugly, not sure like that if people can really solve it explicitly. But you can compute the index for these things if you know like the geometry and yeah.
Maybe basically, if I can make a comment, the goal is more to find like how many zero modes are there. So you have to assume that they are there, and then to find something on them. So it's more, that's why we assume we have a solution, and then using the fact that you can extend it to something without a boundary, non-compact anymore, but without a boundary, it's a useful tool. You can compute the index, and then the problem is that the missing ingredient is like
Yeah, okay, I can just briefly say. So the idea for this was that we use the index theorem in order to say we do have zero modes, because that was the complicated thing somehow to say that there would be something satisfying this APS boundary condition. But with the index theorem, we can actually compute this. So knowing that we have this, we have index, so this difference of these dimensions that I erased over there is non-zero. And then sort of what we assume is that again something like Aharonov Casher will hold, that there will be something, they call it vanishing theorem, that only one contribution is there and the other one is just zero. So what we wanted to show is that one of G plus, G minus, and on the flux will be just zero. And for that, we want the argument principle. So we sort of look at the function G, which has to have two layers. And so that would be that you look at R2 and you remove a hole. So you want that outside of a certain circle, BR, that the function has this decay. And it would take sort of along this BR, and then along this hole, and then back again. So then we want to compute the integral over this space. The G is analytic here, so there will be no poles. And then if we look at the integral along this whole curve, C, we split it in two integrals, one along this BR and one along this, let me call it omega, d omega. And then I know that along the C, that inside that by the argument principle, this would be the difference between the zeros of the function here and the poles. So zeros minus poles, but they are both like, this is difference of two positive numbers. So we know that there are no poles. It's an analytic function there. So this is greater or equal than zero. Now we have this decay at infinity. So if we compute this this winding number, sorry. So this is like integral of G over G prime. So and that gives me the winding number. So if for the VR, we want this decay there. So from that, like doing a couple of computations, we would know that this one is less or equal than -1 because we want the decay. And then we want to use the boundary condition here. And using the boundary condition here would again give me that this also has to be a negative if I'm on the inside. If I'm we would get that like this, we have zero on the right hand side, but something that is smaller than it, but is supposed to be greater on the right hand side. That such a G does not exist. So we have only the zero modes of this other one. But the problem was that we have this linear combination of AJ, and we don't really know what that is. So we get some zeros on the boundary, and this is where we sort of started to work harder. So that was, and this extension to like a cylinder was the idea that if we know that we can extend these zero modes, that we would not have accumulation of zeros towards the boundary. And if we have just like a zero at the boundary, which is isolated, then we could take the curve so that it sort of avoids this zero somehow, and we can somehow treat that. So that is sort of the idea that we hope now is finally gonna work. Not too sketchy. That it was understandable.
Another question?
Flexibility do we have under isomorphisms of the domain? Instead of having a cylinder, can we have some isomorphism which is almost cylinder?
I'm not sure exactly what do you mean, like that. So what actually happens in our case is that we don't have the cylindric structure at all. And this is why we also have a bit more problems, because now our B depends on this R. So you cannot really just impose this. So actually, when we want to glue things to this, we actually have the plane and then we glue them like this. But what exactly do you mean like that?
So instead of an exact
Like-
cylinder structure, if you just had some kind of a normal coordinate nearby, which is more general, would the same work? Or
Yeah, you would get this dependent on how splits things. I mean, to be fair, there is a work by Melrose, and he somehow uses even more like a broader formalism, and I've never really been able to understand it. And they actually might be able to find some relations to this, but okay, I don't really know much about that, like what they do there.
The rule basically is that you have locally need the boundary, but it's a natural system of coordinates, so you take the boundary and then normal.
Yes,
right?
Yeah,
And this will always be conformal equivalent to a cylinder. It's not a cylinder. It's just locally conformally equivalent to a cylinder. That's why they have this sigma. They have coefficient.
Yeah, the sigma is more
Okay.
from the Dirac structure, and then you have the V, which is giving the problem.
yeah.
But you can consider, for example, conical stuff.
You're not even the two poles is a problem, so.
But what I want to say. The thing about this boundary condition and why we also like move to this infinite mass boundary condition is that the infinite mass boundary condition is more friendly with the Riemann mapping. I didn't end up talking about it, but there you can actually use the Riemann mapping. Here, the problem is that if you do the Riemann mapping, it's like a conformal change of coordinates, and then you get like the conformal factor here in front of D, outside of D, and like for the zero modes, it's basically like, okay, this is fine because we can just multiply U by the factor that we have here. But the problem is that the factor that like the scale that we have here is different than as the boundary operator scales this B. So if you do this conformal change, that would be like the factor to minus 1, but there will be something like A to minus 1/2. So this was the complication why we can't really use the like conformal changes or something like that. Not sure if that answers your question. I guess we sort of diverted. Yeah, we can also discuss that lunch.
Another question? Some questions of the people online? Then let's just say. Yeah, let's just say, no, it's other fact.
Yeah.
Somebody raised the hand.
No, it's about the board. It's not.
No,
the
but-
question.
Ah,
No, I'm seeing you.
Okay.
Then let's say thanks again to Marty.
thank you.
I would like to say some words